Okay, can you hear me? Yes. Well, first of all, I'd like to thank the organizers. It's always a great pleasure to be in Paris, and the conference for me was really incredibly interesting. Second thing, okay, what I'm going to discuss, well, okay, I have this nice thing here. Now, as you see, I mean, I'm going to discuss about multiple point source detections in CMB. So in some sense, this is based upon two companion papers. One is more mathematical, and it's going to appear on a journal which is called Bernoulli this year, and involves other people into Vergata, but not only into Vergata. Then there is another paper which is more, you know, it's really the one with the application to CMB data, which is not been posted on the archive yet, but it's almost finished with these other people like Carron, Buzzelli, and Vittorio. But what I would like to explain right from the beginning is that also given the nature of this conference, well, one should see this application to point source detection in CMB data as an example among others, by which I mean that on one hand, I hope that this is a sort of a general procedure that you could use in other framework, for instance, like source detection in gamma ray sky or in a polarization maps or so on. But moreover, in the discussion, I would like to go through the different steps of the procedure, and some of these steps hopefully have a more general interest, and in any case should be the occasion for me to discuss broader issues about inference in cosmological data, okay? So, okay, this is a picture that I guess you've seen many times. So this is a real CMB map, one of the latest Planck release. Now the next one is actually a simulation with a lambda CDM model. The choice of colors, unfortunately, is slightly different, so they don't match exactly. But this is just standard best fit Planck parameters, with one difference that in these maps, in the simulations, there are more than 1,000 simulated point sources with a realistic physical model. Okay, so there are no foregrounds, no galactic cuts and so on. Everything else is supposed to have been cleaned, but there are point sources above. And this is just to show you that actually point sources are quite difficult to see in practice, because here there are really 1,000 or more, but you don't see any difference in the map. Okay. Now, so you want to test for the presence of these point sources, for instance, after the map has been cleaned by all the other foreground. But this is part of a more general statistical problem, which has become extremely popular in the statistical literature over the last 15 or maybe 20 years, which is the problem of multiple testing, okay? Which is quite different from the standard framework of testing either frequentist or Bayesian, as it's taught in standard undergraduate courses, okay? So testing is something very trivial, which you've all seen. So you assume that you want to look for some parameter, then you have some estimate. So you assume that the estimate is like Gaussian or something like that. The true value should be supposed to be here. So if you observe something which is far away from the true value, then either by a p-value or by some credible region in a Bayesian framework, you reject your null, okay? You say, I'm far away from the null, so I cannot accept this, okay? So this sort of framework breaks down completely when you have to run many, many tests at the same time, which is very usual in a number of applications. For sure in cosmology, because when you look for point sources, you may have thousands of them, okay? And so you are going to test jointly the fact that it's 1,000 different pixels that can be a galaxy or something else, okay? But then, for instance, everybody here that was inside Planck, or anybody has been reading the Planck or WMAP papers, may remember a very fierce debate about anomalies, okay? So, for instance, if you go back to this map here, okay, so I think it's somewhere here, it's the cold spot which has brought hundreds of papers, because it's a large cold region which, depending on the statistic you use, 2.5 or 3 sigma is considered to be not compatible with Gaussianity. But and there are other anomalies like this that were found in Planck or even WMAP data before, okay? But of course, there was a very hot debate about look elsewhere effects, okay? Because, nobody has been really looking from the start to this cold spot. We have all run hundreds of different tests on different scales or different features and so on. And then out of these hundreds of different features, you find one which is significant at 2.5 or 3 sigma. So how do you interpret this, okay? So of course, this is you know, it's quite tricky, okay? Because it's not the same thing as a single test as one has been taught at the university, okay? And then of course this appears in many other fields of science. It's very common in genomics, where you run tests to see if a gene explains some form of disease, but you have thousands of different genes, so you study all of them together, and that makes a big difference, clearly. And then of course in particle physics and so on. So there are a number of solutions that you can think of, okay? So for instance, particle physicists, they have a sort of convention such that they, you know, you really accept that something is really significant when it's above 5 sigma, okay? Which makes a p-value extremely small, okay? And this is in some sense similar to what in the statistical literature one would call a family-wise error rate, FWER, okay? Which means simply that when you compute your p-value, you don't compute the p-value of the single test, but you compute the p-value of the maximum between all the tests that you're running, okay? So you want to compute what is the probability that if you run 1,000 tests, the largest of these tests is above some level, okay? So 5 sigma is a sort of ad hoc similar idea, no? So you say, okay, I look at the maxima of all the simple things I've been looking at, and I put a very, very high threshold, okay? But then, in some sense, this is not the best possible solution for a number of reasons. 2 are obvious. One is, okay, fine, you put a threshold which is so high. This is conservative. You are quite safe in some sense. But on the other hand, you don't have good power at all, okay? Because you need really very strong signal to see something, okay? But then there is something which is more subtle and more important, okay? So think back about point sources, okay? So let's say that we look at the maximum, so we fix a very high threshold, like 5 sigma, okay? Now, this means that if you have a single value at 3 sigma, you say this is not significant, because out of 1,000 tests, 3 sigma is not significant. But why is this tricky? Because it's not at all the same story if you have a single test that gives you 3 sigma, or if you have 500 tests out of 1,000 that give you 3 sigma. Is that clear? So if you just fix such a huge threshold, you do not really take into account the multiple nature of the problem, okay? Because if you run 1,000 tests, and then there are maybe half of them that give you a 3 sigma value, then at this stage it's quite hard to say, well, okay, 3 sigma out of 1,000 is not significant. Well, it's not significant in one case, but if you have 500, then this is telling you something, even if each one of them on its own is not big, okay? So you really need to take into account the multiple nature of the problem, okay? So then this is just general multiple testing in the statistical literature. But then if you go to specific issues in CMB or more general in cosmology, you have even more difficulties. And the difficulties, I mean, some of the difficulties are listed here. So for instance, the outcome of the single tests are not independent. So, you know, in the first instance that you want to do in CMB, you look at the maxima of the map and see if they are compatible with Gaussianity or if they can be point sources, okay? But the single maxima are not independent one from the other, okay? Which makes a big difference, okay? Then the other point is that the number of tests itself is random. So you do not know in advance how many tests you are running, because you do not know how many peaks you will find in the map, okay? And then, of course, there is the biggest, I mean, for me, the single biggest and actually even most interesting issue when one deals with cosmological data is cosmic variance, no? Because as has been mentioned in some talk this week before, in a sense, I mean, all statistics theory has been developed under the assumption that you repeat the experiments. Either Bayesian or frequentist, everybody was thinking about the fact that you repeat the experiments and you get multiple values, which never happens in cosmology. In some sense, you have a single realization, okay? So how all the criteria that have been devised to decide whether a statistical procedure is good or bad work on this repetition idea, which in some sense does not appear in cosmology. So how do you deal with cosmic variance, okay? Okay. Now, more precisely about multiple testing in CMB. Well, okay, so we want to find residual point sources, that's clear. We want to implement a multiple testing scheme, so to try to address this problem that I've been mentioning, the fact that you run hundreds or thousands of tests at the same time. Okay, well, okay, there are some tools that I'll discuss later on, and then of course, this your noise is my signal is something that you may have heard already a lot of time. Clearly, in practice in CMB, one usually is interested in CMB and see point sources for grounds are noise, okay? But just for the purpose of this talk, we go the other way around. So we pretend that CMB is the noise, and we look for the signal, which are the possible point sources, because we want to subtract them, okay? Or see if they're still there. Now, the other thing that I wanted to say, okay, it's just, of course, this is not at all the first paper which has been using wavelets. I'm going to use needlets, which are a form of wavelets, I'll discuss in a minute. It's not the first paper at all which has been using wavelets for looking for point sources. Actually, I've been working on that myself for a few years with other people like Frude and others, but also Jean-Luc Stark, which was here, has worked of it a lot with other people, and then Enrique Martinez-Gonzalez and others. Okay, there are a number of other papers that do wavelets for point sources. That have been a number of papers like this have appeared in the last years. Okay, so what we are going to use is a procedure which was already known in statistics and called STEM. Okay, STEM stands for smoothing and testing multiple hypotheses. Okay. It's basically a 4-step procedure. What I would like to do now is to discuss the steps one by one, and this, is what I told you 10 minutes ago when I said, okay, apart from the specific multiple testing issue, we try to discuss other tools that may be hopefully of interest even outside the testing and outside CMB. Okay? So the steps are, first of all, you smooth the map, by which I mean you filter the map in practice to improve the signal to noise and for other reasons that I will discuss. Then you look for the candidate peaks. Well, that's just a numerical issue. That is, you look at the maxima. You look at the distribution of this maxima that you need for the procedure that you want to implement. And then you implement a multiple testing procedure that takes into account the issues I've been discussing before. So the fact that you want to control jointly what happens for all the tests together. Okay? So let's go step one. Step one is filtering of the map. This is going to be done by needlets, actually in practice Mexican needlets. So needlets are a form of wavelets which have been introduced now a little more than 10 years ago, 2006, and have been used in a number of different applications in cosmology, like integrated Sachs-Wolf effect. On Monday, there was the talk by JFC, not JFK, but on... I'm not Jacques either. Sorry? I am not Jacques But I wrote JFC, not JD. So I noticed the difference. Okay, so that's, okay, I was saying, okay, well, I think first application was this integrated Sachs-Wolf, then map making, it's this needlet linear combination, but then many others, look for non-Gaussianity, there is the needlet B spectrum, there is the needlet KSW, W is here, K was here, but now has gone out, and has never been here, at least in this week. Then asymmetries, north-south asymmetries. Then there is this application to isotropy and Minkowski functions. This is what Robert Adler has been discussing also 2 or 3 days ago. I'm going to show you one application in the Planck 2016 isotropy paper. And then other applications like polarization and gamma rays, ultra-high energy cosmic rays. It's been, there are a number of references. So what are needlets? Okay, something in the end, skipping quite a bit of details, the story in the end is very simple, okay? So everybody here, and for sure everybody that has ever seen a CMB paper, knows the first equation, okay? So you have fx is a field on the sphere, random. You can expand it into spherical harmonics, okay? So what does it mean? It means that you can actually decompose the field into orthogonal components, FL, which live at different frequencies, at different multiple. So you have the field, you look at this field, and you look at the components that live at different scales. Small l is small multiple, and so large scale. High L, small scale, large multiples, okay? So in practice, this you can view what? Now, these brackets are not what you use for the expected value. This is inner product, okay? But this is just, it's just a mathematical formalism, very trivial to say that these components FL can be viewed as the projection of the original field by means of this Legendre projector, okay? So this is just like an operator which takes your field and gives you the multiple component. It's what everybody does with ILPICs, okay? So you take the field, you do the projection with the spherical harmonics, you get the ALM, and you reconstruct a single component FL. So this takes the field and projects into the different frequencies, okay? Now, this is just a form of Fourier analysis on the sphere. As always, when you do Fourier analysis, what you get is perfect localization in harmonic space and very bad or not at all localization in real space, okay? That's the same as if you do a Fourier transform on the line. In the sphere, it's slightly better, but not so much better. So it's perfect localization. This component lives on a single multiple, so on a single scale, on a single frequency, but loses all the information, or not all, but almost all the information on pixel location, okay? Now, of course, for CMB, this is a very big problem, because you know that you have like galactic masks, regions which are not observed, and if you want to look for point sources, of course, what you want is to keep the information about the directions in the sky. You cannot lose it, okay? So the idea is, what do I want to do? I want to get better localization in real space. How do I do that? Well, you cannot get something for free, for nothing, okay? So what you do is you pay a bit in terms of localization in harmonic space. So you are willing to lose something in terms of localization in harmonic space in order to gain as much as possible, a lot, hopefully, in terms of localization in real space. That's the very simple idea behind the story. So how do you do that? You build another projector, which is this one here, okay? Where basically you do no longer project on a single multiple L, but you project on some nearby multiples, okay? So here there are just some technicalities. So this single PL would project you on a single multiple, okay? You take an average of these PLs, okay? With some weight function B, L over Bj. So B, this capital B here, is nothing special. It's just a parameter that you can fix, that you choose. Say that it's 1.1. Larger than 1, it's a fixed parameter, okay? J is a scale parameter, so it's like a multiple. Really, B to the J is like a multiple, okay? So high J means high frequencies, small scales, okay? Low J, low frequencies, large scales, okay? And then, of course, the key issue is the proper construction of this function B. This function B must have some technical properties. I'll discuss them in a minute, but basically it must be very smooth, so have a lot of derivatives, very concentrated around the multiple you're interested in, and then some more technical properties, like a property which is known as partition of unity and so on, but about that you don't care. So let's just say that you have to choose this function in a clever way, okay? Then you project your field with this projector, and you get these components, Bj, which then are what? Again, they are clever, hopefully clever, averages of the single multiples, okay? With this function Bj, fine? So, of course, the crucial step is the construction of this function B, which must have some properties. There are some alternatives. Standard Needlets have a construction which is, now well known, but a bit not analytic, so a bit more complicated to describe. Mexican Needlet is easier to describe. They have advantages and disadvantages. Anyway, all these things are now implemented in a number of packages, and they're even available on ILPICs. Okay, so they are, easy to use. So what are the advantages of this construction? Well, okay, there are quite a few, numerically and from other points of view, but there are two things which are the most important in my view. One is that, what you can imagine. As in general for wavelets, what I said before, you have lost a bit, but just a bit in terms of localization in multiples, so your components are no longer living on a single multiple, but on a number of nearby multiples that you can control, that you decide what they are, okay? But you have gained a lot in terms of localization in real space. Let me show you a picture, okay? So that's an example of needlet. So the tails are going down really quickly. They have a property, I mean, this is going down like nearly exponential. So they can be defined rigorously mathematically, but the idea is that they are very much concentrated, okay? Which of course is very useful when you want to handle masked data or when you want to look for point sources or things like this. Okay? So you do have a lot. The spherical harmonic transform is not local. I mean, if you have a masked CMB map, then this is going to affect the multiple component everywhere, okay? This is not the case for needlets, okay? If you are sufficiently far away from the mask, which is quite small, like 1 degree away from the map, then you won't basically see it in the transform, okay? And so, but the other property may sound a bit more mathematical, but for me it's even more important and quite surprising. So I remember that in the beginning we said that there was this big cosmic variance issue. So the point is that when you take these transformed fields, okay, if you look at 2 points in the sky, and then you go at high frequencies, these 2 points basically become uncorrelated, and then it's independent in the Gaussian case, okay? So this has not to do neither with the real space localization, nor with the frequency space localization. Not with the real space localization, but because if you take a Dirac delta function, which is perfectly localized, then you get the field here and here. This is not independent at all, okay? But even if you take like simple top hat, no? So you just take the harmonic transform of the CMB and you drop the first 100 multiples, you don't have the same property. So you have some form of uncorrelation, but much weaker than this. So this is really in the construction of the function B, which is smooth, okay? And this is clearly crucial because, you know, when you beat cosmic variance, there are a number of, to some extent, then there are a number of things that you can do, okay? So this is the shape of a standard needlet. This is the shape of a Mexican needlet. The story is just that they oscillate, they get concentrated around their center, and more concentrated as J grows larger. So for instance, this screenshot is taken from the Planck 2016 isotropy and statistics paper, okay? So these are what? These are the Minkowski functions that were discussed in Adlerstorff, okay? So boundary length, excursion area, and Euler-Poincare characteristic. But they are evaluated on the needlet components. So first of all, you gain much more statistics because you no longer have a single map, but you have a number of filter components, okay? But more than that, what you have here, okay, this doesn't show up so much in this picture, but the point is that if you look at the paper and you look at the scales here, the scales in this plot are not the same. So these halo are just confidence band, okay? So they look, this is as the scale gets, the J gets larger and larger, so the scale gets smaller and smaller. It looks like the halo are of the same magnitude, but they're not, because the scaling factors on the y-axis are different. There is a factor 1 here, 4 here, 12 here. So it means that when you go to higher and higher scales, the confidence bands become narrower and narrower, more and more concentrated, okay? And so, in this sense, you beat cosmic variance, okay? So you get tighter and tighter constraints on the needed filter maps. Is that clear? No. So the variance, I mean, this is the Minkowski functions evaluated on needlet components. This is at some J. This is a J that corresponds to small multiples, like 16. This is a J that corresponds to multiple 64. This is a J that corresponds to multiple 2056, and you can go higher and higher, okay? Then when you compute these Minkowski functions on these components, their variance on a single map becomes smaller and smaller, okay? So they are closer and closer to their expected value, and then fluctuation becomes more and more significant. This is a crucial property also for what I'm going to discuss afterwards. Now, I'm going very slow. So, okay, so for instance, just to give you an idea, this is a CMB temperature map. This is the beta map, the filter map. So what you see is that in some sense this lives at higher scales, okay? So it's more wiggly, and that's natural. What is more interesting is the following. So think of it in terms of signal to noise. So this is a simulated map. Here there are 7 sources. These red circles are artificial, are just put here to help you see them, but they're not in the map. So this shows you that the sources are very weak. You don't see them at all. This is the filter map. Now the sources have become very, very much more apparent, okay? So after filtering, the sources become much more visible and signal to noise improves a lot. This is confirmed by this plot here. So for instance, So this black line are the original sources, which are a signal to noise centered around 2, ranging from 0 to 5. And then the other color lines, they give you the signal to noise ratio as you go to higher and higher filter map. So for instance, for this J38, which is the highest values corresponding to the highest multiples in Planck, you see that the signal to noise has improved a lot. It's much more on the right. Okay? So this is step number 1. Step number 1 is filter the map with these needlets. Then step number 2, compute these are, okay, let's do step 2 and 3 together. Compute the maxima, okay, that's just numerical issue. Find their distribution, okay? So what is the expected distribution of the maxima in a Gaussian map? Okay, this is something that has been studied in mathematics for a long while, and even in cosmology, starting from the 80s. I think the first paper is a paper by Bardeen and others, where they study the expected value of the maxima for Gaussian fields, okay? So there are some nice mathematical tools to study these things, which I'm not going to discuss. But what we did here is 2 things. First thing is to find the expected value of the maxima for this, the distribution, or the expected distribution of the maxima for these needlet filter fields. Now, this expression may look, for sure, horrible, but on the contrary, it's very easy to implement, because there are 2 things, basically. Capital phi is just the Gaussian distribution function. Small phi is the Gaussian density function. And then there are these parameters, K1 and K2. So these are just basically related to first-order derivatives and second-order derivatives of needle fields. They have a very simple analytic expressions in terms of the CL, of the angular power spectrum. So this means that if you give me the CL, either sample CL or lambda CDM CL, then with very simple operations, summing them with some weights in terms of L, you get these parameters. And then you have the expected distribution of the maxima, okay? So that's fine. What is more surprising is the second point, which is related to what I was telling you before. So not only you can study the expected value of the maxima, but you can study also their variance, and you can prove that this variance goes to 0 at ij. So it means that if you have a single realization of the CMB map, and you study the filter component at ij's, in this single realization, the sample distribution of the maxima is going to converge to the population distribution, okay? And this is what I'm going to show in these simulations here. So the red line is the theoretical distribution. The yellows are the simulations of 200 CMB sky with lambda CDM. So you see that this halo is very small and gets smaller and smaller when you go to ij. So if you take a single sky and you look at the empirical distribution on a single sky of this maxima, it's going to go to this theoretical value. Okay, which is something nice for me. Okay, so this is point. Okay, how to do the proof? I mean, if you want to discuss it, I'm happy. It's what Adler would call, in the book by Adler and Taylor, there is a big result called the expectation meta theorem, which is based upon earlier results like Katzenreis formula. I mean, there is a lot of very nice mathematics behind, but you can do these computations really explicitly, and they do work in practice. Okay, now step 4. These were step 2 and 3, is the multiple testing issue. So multiple testing, what's the point? So the big thing to remember is this false discovery rate. So what's the idea behind? The idea is, okay, I will have to run maybe 100, maybe 1,000 different tests. I cannot pretend that I will get the right answer in every single test, okay? I have to accept that I get something wrong. So rather than go looking at like the p-value for the single test, what I want to control is this false discovery rate. What is it? So the point is, I have 1,000 tests to run. What I'm going to accept is the fact that if I claim 200 detections, no more than 10% of them are wrong. Okay? So I do not control the result on the single test, but I control the proportion of errors that I do. Okay? So think, for instance, that you look for these point sources, and then when you find the point sources, you send like a message to all the community and tell them, okay, move your telescope, look in that direction, there is a point source, okay? Now, these people, of course, they are unhappy if you waste their time, no? If you ask them to look somewhere where there isn't anything, no? Maybe think about gravitational wave detections, okay? So you pretend that you found some gravitational wave in the signal in some direction, okay? Then if you do so, you send a telegram, then hundreds of telescopes in X-ray infrared, optics, so on, they turn their way and start to look in that direction. Then if there is nothing, they're not going to like it, okay? So in some sense, you want to be very conservative, but not too much, because if you're too much conservative, then maybe you miss some occasions to see something. So the idea is, I cannot assure you that on every single case, I'm going to give you a good hint to look in the right direction, but the number of errors that I'm going to make, so the number of times that I'm going to waste your time, is no more than alpha%, okay? 5% or 10% and so on. And you choose alpha, okay? So that's the idea of the false detection rate. You do not control the single test, but you choose a threshold in such a way that no more than alpha% of the times you claim a detection when there isn't any, okay? So there is a very nice trick introduced by these guys, Benjamini and Dockberg, in the mathematical statistics literature, to control this false discovery rate. So what is the idea? Okay, it's described in the slide, but I'll try to draw a picture, assuming that it's easier to get. So by the results in the previous step, now you know the distribution of the maxima, which means you know the p-value of each maximum, okay? So if you have a maximum at 4 sigma, you know that the p-value is 0.001. This is not the p-value of a Gaussian field. Even if the field is Gaussian, clearly the distribution of the maxima is not Gaussian, even if the field is Gaussian. Of course, no, because you look at points which are especially big, so the distribution is no longer Gaussian. But you know the distribution of the maxima. So for every local maximum that you found, you know its p-value exactly. Okay? So you arrange these p-values in increasing order. So these are the ones that are really small, then these ones are larger, and so on and so forth. And you can prove that you get a convex line like this, which goes between 0 and 1. Okay? So these are just the p-values that you have observed. Okay? You have observed 100, 1000 local maxima. You compute the p-value for each of them, and you put them in this line. Okay? Then you fix this alpha. How many false discoveries are you going to accept? 5%? Okay, then alpha is 0.05. And you draw a line with slope 0.05. Okay? Now, the two will cross somewhere. Okay? The values that are below the line, these are p-values that are really small. Okay? Then this, you say this must be point sources. These others can be small, but not small enough. Okay? And so you do not qualify them as point sources. Is that clear? If you think about it a minute, it makes sense that this should control the... No, maybe a minute is not enough. If you think about it for some time, the proof that this controls the false discovery rate is hard. But the intuition that this should work it makes sense, no? Because in the end, you know, for instance, here you may have like 100 sources, okay, with some p-value, and with this parameter alpha, it's like, I mean, if the field was just purely Gaussian, the p-values would be like this. So these are there would be a straight line at 45 degrees if you had just a Gaussian field. So you get this threshold value here, which in terms of the Gaussian field corresponds to alpha% of the sources that you're really going to accept. Okay? So this is the numbers, the one that you expect to be false. And the others must be true. Okay? Okay, that's the intuition. So that's Benjamini-Hochberg, that's the false discovery rate. Then at this stage, okay, so I have like something less than 10 minutes, 7 minutes. Okay, so okay, you may have suspected that I like mathematics. So at this, then in this paper we try to prove a number of results apart from doing simulations, and to prove what? To prove that first of all that you can actually control this false discovery rate, and then that the procedure has power, so that you see the sources when they are there. Okay. Now the definition of you need to define errors and not errors. This is more tricky than one could think. Okay. This is the same as happened with the Planck papers, okay? Because of the beams and everything else, even when there is really a point source somewhere, and you find it in CMB, they're not exactly in the same pixel, okay? Because they, by the beam and other issues, they can be moved a bit, okay? So in order to define when you've seen the source or not, you need like a tolerance parameter, okay? Because how do you define that you've seen a point source? You look at the Planck data, you see a maximum, you decide this is a point source, then you cross-check with some known catalog of point sources, okay? But then they are not exactly in the same location. So when do you say, okay, this was, I've seen these point sources or not? When one has to fix some parameters like tolerance parameters, so a distance between the catalog and the Planck data which is acceptable given the beam and so on and so forth. Okay, this is just to say that the definition of detection and non-detection is a bit tricky, but maybe I don't have time to discuss all these things. Let's say just that the false discovery rate I have discussed. The power is what? Just the proportion of point sources that you see. So you have power 1 if you see all point sources that are in the map. You have power 50% if you see half of them. Okay, that's the rule. That's quite simple. Okay, after that you can prove some. Okay, let me skip all this. Okay, these I will skip. Well, basically there are two things that you can prove. Then I go back to simulations. First of all, that the procedure works in the two senses. It works in the sense that it does control this false discovery rate. Okay, so that's the second line. So if you do this Benjamini-Hochberg on this spherical field with the p-values, the number of false proportion that you are going, the false detections that you are going to get is actually bounded above by this alpha that you choose. So in the worst case, it's this value, otherwise it's smaller. Okay? So that's one result that you can prove. And the second result that you can prove is that when you go to very high frequencies, so you allow J to get larger and larger, so you allow the maps to see higher and higher multiples, eventually you see all sources. Okay? Okay, these are theoretical results that may not convince you, but maybe the simulations will be more illuminating. Okay, so these are sort of realistic models of point sources at different intensity being defined in terms of sigma C and B, so sigma to noise, okay? So basically, okay, the number of point sources that you actually see depends on the alpha you choose. Here alpha is in the order of 5%. Of course, if you are ready to accept more false detections, then you're going to see more point sources and the other way around. With this value, you see that starting from 3 sigma, we see basically 70% of the sources, and at 4 sigma, we see almost all of them. But maybe this is clearer. So let me show this. The plot on the right, this is the false discovery rate. So the dashed line is the theoretical value, and the continuous line are the simulations. So there are 3 different models where we inserted in the map 1,000 or 3,000 or 5,000 different point sources, and then we check what happened. And what happened is that in all cases, as you see, the false discovery rate from simulations is below the theoretical bound. Okay? So the plot gives you different value of alpha. As you go from left to right, you are taking alpha to be 002, 004, 006, 008. So you're going, it means that you are willing to accept 2% or 4% or 6% or 8% of false detections. And you see that in practice on the simulated data, the number of false detections are below this bound that we imposed. Okay, so it goes better than predicted. No, I mean, it's an upper bound, so it's not better than predicted, but it's below the upper bound. And then this is the power. So this is, again, 1,000, 3,000 or 5,000 point sources included. How many do we see? Then this parameter J should be, I mean, it would have been better to put a sort of equivalence in terms of the multiples, okay? So the upper J here is basically, corresponds to the highest multiples in Planck where the noise is not really relevant. So I would say around 1,300 or 1,500 at most, then noise becomes more important. While 35 is below 1,000, okay? So you see that if you go to use maps that are over 1,000 multiples, basically we see 99% of the sources that have been introduced. Okay, very last thing, I'm going to have 1 minute. Very last thing I would like to tell you, okay, that's similar. This is the application to Planck real data. So I've not discussed in this talk foreground, masked regions and so on, but all these things have been taken care of. In fact, in a loose sense, because of this, to some extent, okay, this is a bit idealistic, okay, but just with some idealism, because of this localization property of the needlets, to some extent you can think that the effect of the masks and cut regions is just in an F-sky fraction. This is not entirely true, as everybody who's been working with needlets knows. So the story is not really as simple, but morally, it's you know, this gives you an idea, okay? So dealing with the other, I mean, we did cover all the Planck sky model with all dust, free, synchrotron, and everything, and did the application. Now, this, you know, it's in this sense, it's a bit a pity that I'm being videotaped because you know, these results are still preliminary, and we didn't even post them on the archive, so they should be taken with more than a grain of salt. Anyway, what we did is to apply these things to the WMAP, to the Planck maps, meaning both the first release, like 2013, 2015, and the latest, like the imprinted maps that had been released in July. Okay? So in a nutshell, the idea is, so I mean, as I wrote them, do not quote them, and it's just preliminary to give you an idea of the method. So the bottom line seems to be the following, that actually the latest maps are very much improved. Improved, so in this term, with respect to the previous ones, because still in the 2015 release, we had a number of significant peaks that we could see in the maps, okay, which range, you know, that there are these 4 different methods, which are SMICA, NILC, Commander, and CEB. So these were ranging from 55 to more than 100 according to the method. And you know, for instance, these 55 point sources that were detected in a map, 53 of them we could find an analog in a point source catalog. So then in the latest release, the situation is improved a lot. I can make Jean-François happy, saying that the best map in absolute term is NILC, where we have 0 detections and 0 correspondence, so there doesn't seem to be any point source. But even for the others, for instance, for 7 there are just 3, and we didn't find the corresponding point sources in the catalogs, which means either that these peaks are just fluctuations. 11 for SMICA, 7 of which had correspondence. For Commander there were the most, 70, but only 8 had the correspondence. So this result we are not still sure how to interpret. Okay, one end it may be simply that for this case our method did not work so well. Another possibility is that there are not really point sources, but because all these maps now have been painted, it could be the case that a little bit more peaks than expected have been inserted in the map. These numbers, in any case, for all the maps should be considered very, very small, because the real point sources that were subtracted from the beginning of the Planck pipelines were in the order of several thousands, first of all. And secondly, if you have a map at the Planck resolution, which has 6 million pixels or more, then just out of Gaussian fluctuations, you expect several thousands local maxima, okay? Several thousands, okay? It's a computation that you can do easily, but really several thousands local maxima, okay? So the tests that were run here were in the order of several thousands, and just very few p-values were found below the threshold. So anyway, the bottom line is, as everybody knows inside here, Planck temperature data have been very much studied and are now very much understood. So for sure, it wouldn't be worth the effort to do all this just for the temperature. The temperature you should view like really sort of expository application. Our idea is, first of all, to apply this to E-mode maps, so polarization, and then to maps which need not be CMB or things like this. But clearly, I hope that some of this idea, like some of these ideas concerning filtering or multiple testing and so on, have a broader interest outside these specific problems. And that's it.